Hello friends, good morning. In the unit protection, so far I have covered generator protection and transformer protection. Today I will discuss bus protection. Bus protection or bus bar protection. First let us see what is this bus or bus bar. Definition is, it is a node in the form of metal strip to which all the incoming and outgoing lines are connected. So here you can see it is a metal strip that is a node. To this all the incoming and outgoing lines are connected. So this is bus bar or simply bus. So here I have shown to this bus two generators are connected. That is generating station. Then from other power area, one line is coming and there are four load areas to which outgoing lines are there. So it is a node in the form of metal strip to which all the incoming and outgoing lines are connected. Now let us see what are the salient features of this bus protection or bus bar. First is, under normal condition and external fault condition, summation of all incoming current is equal to summation of all outgoing currents. So mathematically I have written summation I is 1 to n, where n is number of incoming lines, is equal to summation ij is equal to 1 to m, where m is outgoing lines. So here all the incoming current will be equal to outgoing current. That is under healthy condition. Under external fault condition also this equation is valid, but difference is current magnitude is very high. But if bus fault occurs, that is say somewhere here, then what happens? Whatever current is coming here, that is diverted to the fault. So outgoing current will be very small or outgoing current will be almost zero. So this equation is no longer valid when bus fault takes place, that is internal fault. You can say it is bus fault occurs. Second silent feature is, when bus fault occurs, all the incoming and outgoing lines are disconnected simultaneously, so that this fault is disconnected. So all the incoming and outgoing lines are disconnected. Third silent feature is, when bus fault occurs, the short circuit MVA is very large. Short circuit MVA is very large means fault current is very large. The reason is, this bus is near to the generator. So when bus fault occurs, current from this generator from this incoming line is diverted to this fault. So fault current magnitude is very high. Therefore, short circuit MVA is very large. Next point is, when bus fault occurs, a large area is disconnected. So here it is obvious, when bus fault occurs, we have to disconnect all the incoming lines and outgoing lines. So power transfer to all these four areas or whatever areas connected to this bus, whatever areas are associated with this bus, they will be disconnected. So large area of the power system is disconnected when bus fault occurs. Next is, when bus fault occurs, transient stability of the system may be disturbed. Transient stability of the system may be lost. The reason is, but for transient stability study, we refer to the swing equation. Swing equation is m d2 delta by dt square is equal to accelerating power. PA is accelerating power, that is equal to PM minus PE. PM is mechanical power input and PE is electrical power output. M is inertia constant, delta is power angle. And this d2 delta by dt square represents the swing of the power angle. Now when it is a load bus, and fault occurs, so P will be 0. All the loads will be disconnected. So accelerating power will be equal to PM. When there is fault on the generator bus, again the reverse swing of the generator will be very large. So accelerating power or decelerating power, that will be very large. Therefore, swing of the delta will be very fast, and therefore there is possibility that transient stability of the system is lost. Next point is about, next silent feature or next point is about the area covered in the bus protection. So I will explain this with the help of one diagram. In this single line diagram, I have shown different components connected in the substation. Few components I have not shown, like coupling capacitor and wave trap. So here, first component after the bus bar, here it is generator, bus bar, then it is current limiting reactor that is used to limit the short circuit current. Then this is PT, it is used for protection purpose. There may be another PT used for the metering purpose. Then CT used for the protection purpose. There can be another CT used for the metering purpose. Then this is isolator, circuit breaker, again isolator, then earthing switch and lightning arrestor. And there are various components connected in the power system, power substation. So faults on all these equipments, that is covered in the bus protection. Faults on current limiting reactor, CTs, PTs, isolators, circuit breakers, earthing switch, lightning arrestor, etc. is covered or comes under the bus protection area. So if fault takes place on bus bar or any of these components, that comes under the bus protection. Now let us see what are the different types of protection schemes or protections provided for the bus. Here I have shown two different protection schemes for transmission line and distribution line. Overcurrent protection scheme that is used for low voltage lines, that is distribution lines. I have already explained the protection of distribution lines by overcurrent relays. So here I have shown three line sections, AB, BC and CD. Relay R3 is an overcurrent relay. Now this can be any type of scheme, definite time by using definite time relay or instantaneous relay or IDMT relay, that is current graded protection or time graded protection or current plus time graded protection. So here R3 is providing protection to line CD. R2 is providing primary protection to line BC and it is acting as backup protection to R3, means backup protection to line CD. R1 is providing primary protection to line AB and backup protection to line BC. Now here if you observe R2, it covers area BC in its primary protection and CD under backup protection. So automatically this bus bar is covered in the backup protection of R2. Similarly, R1 is protecting line AB and BC. So this bus automatically covered in backup protection of R1. Now here we are using this relay for generator backup protection as a generator backup protection or transformer backup protection. So it is automatically covering the faults on this bus bar. So we can see here that by using overcurrent protection scheme, that is IDMT relay or definite time relay or instantaneous relay, no separate bus protection is required because all the buses are automatically covered in the primary or backup protection of overcurrent relays. Now let us come to the resistance protection scheme. This is used for transmission line. Therefore, I have shown two sources, that is sources at both the ends. Again, three line sections, say AB, BC and CD. We have to start relay at both the ends because sources are at both the ends. And normally we provide three-step resistance protection scheme. So if you consider relay R1, it is providing protection to 80% of line, say AB, then remaining 20% plus 50% of next line in second step, and then in third step it is covering remaining portion and 20% of next line. Similarly, we are providing settings to relay R2, R3, R4, R5 and R6. So here you can observe this bus is automatically covered in the second step of relay R1. This bus will be covered in the second step of relay R2 and so on. Similarly, here we are using the relay for generator backup as well as transformer backup. So that will cover the faults on this bus bar. So our conclusion can be like this: the bus, we don't need separate bus protection as it is covered in the line protection or backup protection of generator and transformer. So in old days, previous days, when fault level was not so high, separate bus protection was not essential. But nowadays, fault level is very high, so we need separate bus protection. And that bus protection is provided by using the differential relays that I will explain now. The scheme which is used for burst protection is differential scheme. Now in case of differential protection, current entering and current leaving the protected zone are compared. If there is any phasor difference between current entering and current leaving the protected zone, then the differential relay operates. So here our protected zone, protection zone will be bus bar. So in case of differential protection, we use CTs on both the sides of the protected zone, and these CTs are connected by means of pilot wires, and relay is connected at the equipotential point. So this is the protected zone, that is bus bar. I have shown here 3 incoming lines, 2 generators, 1 incoming line and 4 outgoing lines. So this is the differential circuit, and relay is connected at the equipotential point. Now for providing the differential protection scheme to the bus bar, these are the steps. Number 1, we have to provide CT in all the circuits. So 3 circuits are there in the incoming side, 4 circuits are there in the outgoing side. So we have to connect CTs in all the sides, in all the circuits. Second, CT ratio for all the circuits should be identical, and it is selected according to the maximum current in any of the circuit. So here for example I have taken this current is 500 ampere, 300, 200. So incoming current is 1000 amperes, outgoing current is 400 amperes, 300, 200 and 100. So it is also 1000 amperes. So during normal condition, current entering and current leaving the protected zone will be same. Whatever current is entering to the bus bar, that is going away from the bus bar. So we have to see in which line current is maximum. So current is maximum in this line, that is 500 ampere. So we select CT ratio for all the lines, for all the CTs, 500:1. Then we connect, third step is connect all the CTs by due considerations to the polarity marking in parallel. So these are the polarity markings for CTs connected in the incoming side. This is secondary of the CT. So dot represents current leaving. This is outgoing side. Again CT secondary. So dot represents current leaving. So current leaving is connected here. Current leaving is connected here. So let us say current IA is coming from source side and current IB is coming from the load side. So relay current is IA minus IB, where IA is I1 plus I2 plus I3 and IB is I4 plus I5 plus I5 plus I6 plus I7. So relay current is IA minus IB. So any relay, any overcurrent relay, instantaneous or inverse characteristic relay, when connected in the differential circuit, it acts as differential relay. So operating condition is IR should be greater than I pickup. Now let us check the performance of this scheme for healthy condition, for external fault and for internal fault. So when we take same example, these are the values of current from loads going towards the load. These are the values of the current coming to the bus bar. CT used is 500 by 1. So let us check the healthy condition. No fault on the no internal fault or no external fault. So current incoming, that is IA, I1 plus I2 plus I3. So current from this side, we compare the secondary current of the CT, 500 by 1, it will be 1 ampere. It is 300 by 300, 300 by 500. So it will be 0.6 amperes. Similarly, I3 when we compute from the secondary side, it will be 0.4 amperes. So 1 plus 0.6 plus 0.4, that is 2 amperes. Similarly, we compute current on the secondary side corresponding to the primary currents by using these CT ratios. So we get this as 0.8, 0.6, 0.4 and 0.2 amperes. So it is 2 amperes. So relay current is IA minus IB, 2 minus 2, that is 0. So during healthy current, no current flows, any current is not flowing through the relay, relay current is 0, so relay does not operate. Now let us consider external fault. Now let us assume that when external fault occurs, current magnitude increases 10 times. It increases 10 times. Now it is outside the protected zone. So whatever current is coming to this bus bar, that is diverted to the fault. So current entering and current leaving, that will be increased. 10 times means it will be 20 amperes, this also be 20 amperes. But differential current will be 0. So relay does not operate. Third condition, internal fault. So whatever current is coming to this bus bar, that is diverted to this fault. Again we assume 10 times the fault current, 10 times the rated current. Fault current is 10 times the rated current. So I1 plus I2 plus I3, this will become 20 amperes. All the current is diverted to this fault. No current is flowing through all these lines. So IB will be 0. So IA minus IB will be 20 amperes. Pickup is around, normally it is 0.5 ampere, 0.2 amperes or 1 amperes according to our requirement or circuit conditions. Obviously it will be more than the pickup and relay operates. So here we can see when we are using differential protection scheme for bus bar, it operates for the internal faults only. It remains stable during external fault and it does not operate when system is operating in healthy condition. So that is all about the bus protection. So in this I have covered what is bus bar, silent features of bus protection scheme, and then I have covered the different schemes, that is overcurrent protection, distance protection. They automatically provide protection to the bus bar, no separate bus protection is required. But due to increased fault level, we need to provide separate protection for the bus bar, and that is in the form of differential protection. So I have explained all the features of this differential protection. So that is all about the bus protection. Friends, if you feel this video lecture useful, then please like it, subscribe to my channel, ask your friends, colleagues and juniors to subscribe to my channel for upcoming video lectures on high voltage engineering and power system protection. If you want to make effective and efficient use of time, then read my book on time management. The link for the book is given in the description box. I have launched a useful course for the students on UDEMY. This course is very useful for the students who are preparing for the entrance and competitive exams. The link for the course is also given in the description box. Thank you.